Welcome! In this session, we'll explore the problem titled Subtract the product and sum of digits of an integer. Together, we'll break down the problem, analyze various approaches, and understand how to solve it step by step. Let's dive in. The problem asks us to calculate the difference between the product of the digits of an integer and the sum of its digits. Essentially, you take all the digits that make up the number, multiply them together to get the product, and then add them together to get the sum. Finally, you subtract the sum from the product to get the result. For instance, if the number is 234, the product of its digits would be 2 times 3 times 4, and the sum would be 2 plus 3 plus 4. The task is to compute this difference for any given integer within the range of 1 to 100,000, and return the result as an integer. The output will always represent this computed difference. Let's break down the example where n equals 234. The digits of this number are 2, 3, and 4. To find the product of these digits, we multiply 2 by 3 and then by 4, resulting in 24. To find the sum of the digits, we simply add 2, 3, and 4, which equals 9. The difference is then calculated as 24 minus 9, giving us the result of 15. Another example is when n equals 4421. Here, the digits are 4, 4, 2, and 1. Multiplying these digits gives us a product of 32, while their sum is 11. Subtracting the sum from the product results in 21, which is the output. Now, consider the case where n equals 101. The digits here are 1, 0, and 1. When calculating the product, multiplying by 0 causes the entire product to become 0. On the other hand, the sum of the digits is 1 plus 0 plus 1, which equals 2. Subtracting the sum from the product gives 0 minus 2, resulting in minus 2. This highlights an important scenario where the presence of a 0 in the digits can significantly affect the result. The constraints ensure that n is always a positive integer and within the range of 1 to 100,000, so we don't need to worry about invalid inputs. Finally, let's consider some edge cases. If n is the smallest possible value, which is 1, then the only digit is 1. The product of the digit is 1, the sum of the digit is also 1, and their difference is 1 minus 1, which equals 0. Another important edge case involves numbers with a 0 in their digits, like 101. As mentioned earlier, the product becomes 0 whenever a 0 is present. Lastly, for the largest possible input, n equals 99999, where all 5 digits are 9s. Although both the product and sum will be very large, the difference can still be computed accurately within standard integer limits in most programming languages. These edge cases help ensure the solution works for all possible scenarios. To tackle this problem, we begin by considering the brute force approach. This method involves systematically extracting each digit of the number and calculating both the product and sum of these digits. We initialize two variables, product as 1 and sum as 0. Then, using the modulo operator % and integer division //, we extract the digits one by one. Each digit is multiplied with product and added to sum. This process continues until all the digits are processed, and finally, we return the difference between product and sum. The time complexity here is O, d, where d is the number of digits in the number, which is proportional to log 10, n. As for space, it requires O, 1, since we only use a few variables. Interestingly, this so-called brute force approach is already efficient, operating in a single loop without unnecessary operations or data structures. For this small-scale problem, no further optimization is really necessary. Another way to approach the problem is by converting the number into a string. This allows us to iterate over the digits directly as characters, converting each character back to an integer to compute the product and sum. The steps are straightforward. First, convert the number into a string. Then, iterate through each character, convert it into an integer, and update both product and sum. Finally, return the difference between the two. The time complexity here is also O, d, where d represents the number of digits, but the space complexity increases to O, d, because of the additional storage required for the string representation. Through this comparison, we notice some key observations. The number of digits in a number is proportional to log 10, n, so digit-by-digit operations are inherently efficient. However, extracting digits using modulo and integer division is simpler and uses less space than string manipulation. While the string-based approach may feel more intuitive to some developers, it introduces additional space overhead. These trade-offs highlight that the modulo-based approach is both cleaner and more space-efficient, making it a better fit for this problem. Given the considerations, the chosen strategy is the modulo-based approach due to its efficiency and minimal space usage. This method calculates the result directly in a single pass, avoiding the overhead of string conversion and additional memory allocation. The final algorithm is simple and effective. Start by initializing product to 1 and sum to 0. While the number is greater than 0, extract the last digit using digit equals n%10. Update the product by multiplying it with the digit and the sum by adding the digit. Then, remove the last digit from the number using n//equals 10. Once all the digits are processed, return the difference between product and sum. This algorithm ensures optimal performance while adhering to the constraints of the problem. It's concise, avoids unnecessary complexity, and leverages the most efficient operations for this task. To solve this problem, we need to compute the difference between the product and the sum of the digits of a given number, n. The simplest way to approach this is through a brute force method. We start by initializing two variables. Product is set to 1 to hold the cumulative product of the digits, and sum is set to 0 to accumulate their sum. Next, we extract each digit of the number 1 by 1. This is done by repeatedly taking the remainder when dividing n by 10, which gives us the last digit. After extracting the digit, we update n by performing integer division by 10 to remove the last digit. This process continues until n becomes 0, ensuring that we process all the digits of the number. Once we have each digit, we update the product and some variables. The extracted digit is multiplied with the current value of product to keep track of the cumulative product, and it is added to sum to accumulate the total sum. After processing all the digits, we calculate the difference between the two variables by subtracting sum from product. The final step is to return this computed difference as the result. This straightforward approach ensures that we handle each digit systematically and produce the desired output. This method works because we process each digit exactly once through the iterative extraction process. By using modulus and integer division, we can efficiently handle numbers of any length without needing additional data structures. There are also a few key edge cases to consider. For single-digit numbers, the product and sum will both equal the digit itself, resulting in a difference of 0. If the number contains a 0 as one of its digits, the cumulative product will become 0, which aligns with the expected behavior. And for negative numbers, taking the absolute value of n before starting ensures that the solution remains valid. The algorithm relies solely on two scalar variables, product and sum, to store intermediate results. This eliminates the need for extra data structures like arrays or lists since we process digits one at a time. As a result, the space complexity is 1, making this approach highly space efficient. From a time complexity perspective, the algorithm is proportional to the number of digits in the number, denoted as d. Each digit is processed individually, and operations like modulus, integer division, multiplication, and addition are all performed in constant time. Therefore, the time complexity is d, which is optimal for this type of problem. Given the simplicity of the problem, this approach is already optimal in terms of both time and space complexity. There is no need for further optimizations such as precomputations or parallelization, as they would introduce unnecessary complexity without significant benefit. The existing solution efficiently balances clarity and performance, making it well suited for the task at hand. This Python solution calculates the difference between the product and the sum of the digits of an integer n. The implementation uses a while loop to process each digit of the number. Initially, two variables are defined. Product is set to 1, and total_sum to 0. These will store the cumulative product and sum of the digits respectively. Inside the loop, the last digit of n is extracted using the modulus operator, n%10. This digit is then multiplied into the product variable and added to the total_sum. After processing the digit, n is reduced by removing the last digit using integer division, n//equals 10. The loop continues until all digits are processed, i.e., n becomes 0. Finally, the difference between product and total underscore sum is returned as the result. This approach ensures that the solution runs efficiently, even for larger values of n. Edge cases such as single-digit numbers are automatically handled, as the loop processes the single digit and returns the correct difference, digit equals 0. The algorithm runs in O(d) time, where d is the number of digits in n, making it very efficient. This is the Java implementation of LeetCode problem number 1281, subtract the product and sum of digits of an integer. The code mirrors the Python logic, with a while loop extracting each digit from the number n using modulo and integer division. The extracted digit is used to update both the product and sum of the digits. Finally, the difference between the product and sum is returned. Key differences in the Java implementation include explicit type declarations for variables and the use of Java's int type for numeric operations. To solve this problem, we need to calculate the difference between the product and the sum of the digits of an integer n. This involves three main steps: extracting each digit, computing the product of all the digits, and computing the sum of all the digits. Once we have these two values, we simply subtract the sum from the product to obtain the result. For example, if the input is n equals 234, we start with an initial product of 1 and a total sum of 0. In the first iteration, we extract the last digit, which is 4. We then update the product by multiplying it with this digit, resulting in 4, and add the digit to the total sum, also resulting in 4. Finally, we remove the last digit from n, reducing it to 23. Next, we continue with the second iteration. The last digit of n is now 3. We extract it and update the product to 4*3 equals 12. Similarly, we add this digit to the total sum, updating it to 4 plus 3 equals 7. We then remove this digit from n, which reduces it to 2. In the third iteration, the last digit is 2. We extract it and calculate the new product, which becomes 12*2 equals 24. The total sum is updated to 7 plus 2 equals 9. After removing the last digit, n is reduced to 0, and we exit the loop. Finally, we calculate the difference between the product and the sum, which is 24 at 9 equals 15. So, the result for this example is 15. Now let's look at another example where n equals 4421. Here, we start with the same initial setup, a product of 1 and a total sum of 0. In the first iteration, we extract the last digit, which is 1. We update the product to 1*1 equals 1 and the total sum to 0 plus 1 equals 1. Removing this digit reduces n to 442. In the second iteration, the last digit is 2. After extracting it, the product becomes 1*2 equals 2, and the total sum updates to 1 plus 2 equals 3. Removing this digit reduces n to 44. In the third iteration, the last digit is now 4. We extract it and calculate the product as 2*4 equals 8. The total sum is updated to 3 plus 4 equals 7, and removing the digit reduces n to 4. Finally, in the fourth iteration, the last digit is again 4. This updates the product to 8*4 equals 32 and the total sum to 7 plus 4 equals 11. After removing this digit, n becomes 0, and we complete the loop. At the end, we compute the difference between the product and the sum, which is 3211 equals 21. Therefore, the result for this example is 21. Now consider a simpler case where n equals 5. With the initial setup of a product of 1 and a total sum of 0, we perform a single iteration. The last digit is 5, so we update the product to 1*5 equals 5 and the total sum to 0 plus 5 equals 5. Removing the digit reduces n to 0, and the loop ends. Finally, we calculate the difference between the product and the sum, which is 5 equals 0. Hence, the result for this example is 0. The time complexity of this solution is determined by the number of digits in the input integer, which is represented as d. To break this down, the process of extracting digits is handled within a while loop. Within this loop, we use the modulo operator to obtain the last digit of the number and integer division to remove it. These two operations are performed once per digit, meaning the loop iterates exactly d times. Now, for each iteration, we perform a few constant time operations, multiplying the product by the digit, adding the digit to the total sum, and the modulo and division operations mentioned earlier. Each of these computations takes O(1) time. Therefore, with d iterations in O(1) operations per iteration, the total time complexity of the algorithm is O(d). This efficiency comes from how the loop processes each digit directly without any additional overhead. The space complexity of this solution is O(1), meaning it uses a constant amount of extra memory. This is because the algorithm only uses a fixed number of variables, such as product, total_sum, and digit, all of which are integers. Additionally, the input integer n is modified in place during the process, so no extra space is allocated to duplicate or store the original input. Another key point is that the algorithm does not require any auxiliary data structures like arrays or stacks, which would otherwise depend on the size of the input. Regardless of how large n is, the memory usage remains constant, as we are only working with a small, fixed set of variables. This makes the solution highly space efficient. When comparing this solution to a naive approach, we can see significant improvements in space efficiency. A brute force method might involve converting the integer into a string, iterating over each character, and converting them back into integers for calculations. This would require O(d) time for the iteration and O(d) space to store the string representation of the number. In contrast, our solution avoids this overhead by directly processing the integer, thus maintaining constant space usage. Regarding time complexity, the algorithm remains O(d) in all cases best, average, and worst, because the number of digits determines the number of iterations, irrespective of their values. Mathematically, this is validated by observing that for an input with d digits, the loop runs exactly d times, with each iteration involving constant time operations. As a result, the time complexity is proportional to d, reinforcing that it is O(d), while the space complexity remains O(1). In solving this problem, there are several common mistakes to watch out for. First, not handling single-digit numbers can lead to errors. For example, if the input is just 5, some solutions might assume there are multiple digits and fail to calculate correctly. Remember, for a single-digit number, that digit is both the product and the sum, so the result will always be 0. Next, incorrect digit extraction is another frequent issue. Misusing modulo and integer division, such as confusing n%10 with n/10, can cause infinite loops or incorrect results. Be sure to plan your operations carefully so you extract digits from right to left properly. Additionally, when working with very large numbers, the product of their digits might exceed the limits of standard data types in some programming languages. To avoid this, use data types that can handle larger values, or implement checks to prevent unnecessary calculations. Lastly, edge cases like n=0 or numbers with leading zeros in string-based approaches can lead to logic errors. Handle these cases explicitly to ensure your solution is robust. Now, another common challenge is misinterpreting the problem statement. Some might misunderstand whether the task involves the product and sum of digits or something else entirely. To avoid this, carefully reread the problem and verify your understanding with simple examples. From an interview perspective, this problem also teaches key lessons. Pattern recognition is crucial. Digit manipulation tasks often boil down to extracting, processing, and aggregating digits using modulo and integer division. You should also consider edge case inputs like n=0, n=1, or very large numbers to ensure you haven't missed any special scenarios. Optimization is another area to think about. While brute force is fine for small inputs, larger constraints might require pre-computing results or leveraging mathematical properties. Finally, communication is critical in interviews. Clearly explain how you extract digits and handle edge cases. This demonstrates both your problem-solving skills and attention to detail. There are also several related problems that can help you practice and deepen your understanding of digit manipulation. Of course, LeetCode 1281, the problem we're discussing, is a direct example of this. Another useful problem is LeetCode 7, reverse integer, which requires you to extract and reconstruct digits in reverse order, building on similar logic. LeetCode 66+1 introduces the concept of digit manipulation with carryover logic, which can be useful in more complex scenarios. Finally, LeetCode 258, add digits, focuses on repeatedly summing the digits of a number until you reach a single digit. All of these problems share common themes and techniques, making them excellent practice for honing your skills in this area. To approach this problem differently, there are 3 alternative methods you might consider. First is the string conversion approach, where you convert the number to a string and iterate over each character, converting them back to integers for calculations. This method is simpler to implement but comes with a trade-off of increased space usage due to the string conversion. Second is the recursive approach, which processes one digit at a time by reducing the number in each call. While elegant, this method could lead to Stack Overflow errors for very large inputs, so it's important to consider the constraints. Lastly, there's the pre-computation approach, which works well if the range of inputs is small, such as 1 to 10,000. Here, you calculate and store the results for all possible inputs in advance, reducing runtime to 1 for each query. However, this comes at the cost of higher space complexity. Each of these methods offers unique advantages and trade-offs depending on the problem constraints and requirements. Great job! To summarize, we worked through a number manipulation problem that required calculating the product and sum of digits in an integer. We discussed the brute force approach with its time and space complexities, and highlighted key takeaways for similar problems. Thanks for joining, and don't forget to subscribe for more insightful coding sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!